Well, this is it. This is the last video for this chapter. It's the last video for Physics 12. So last video for electricity and magnetism. It's a very short one too. We're going to look at how we actually send electricity around the countryside from the Kootenays, where it's created for Penticton, over to Penticton. So it's a nice little application of transformers. And I should tell you that the numbers that I'm going to give you for this example we're going to do today, the numbers are made up. They're just sort of metaphorical, just so you can kind of see the concept. So don't take these numbers for the resistance of the wire too seriously, but you can definitely see how this story works. So electric power lines, what's the deal when you have these big towers with wires on them going across the countryside? Why do they do that? Let's look at what it would be like to run a big extension cord all the way from the Kootenays to the Okanagan, trying to deliver electricity just at the voltage you want at 120 volts. So I'm actually going to call that low voltage. So a big extension cord, maybe we'll drape it over some telephone poles just so it's up and out of the way. But what if it was 120 volts from the hydro dam all the way to your house? So again, made up numbers here, right? Don't take this too seriously. But let's say that the wires have a resistance of 0.5 ohms. I just needed a value and I wanted something we can work with. All right, let's power one house only on an extension cord. So that house might need about 10,000 watts. That's pretty typical. 120 volts. Okay, so you do a little P equals IV and divide, and you see that you need to have 83 amps run through that extension cord. This is not going to go well, trying to get 83 amps through your extension cord. So if you just do a calculation for how much heat you would generate in that extension cord, if you just did I squared times R to figure out the heat loss here, remember you're trying to send 10,000 watts down the wire. At this level of current with 83 amps, you would have 83 coulombs per second, or if you want our shopping analogy, 83 customers per second. You'd have 3,000, almost 500 watts of heat loss. 3,500 joules every second, right? That's a huge chunk of your 10,000 watts. Okay, it's about a third. So when you look at what happens at your house, you'd only have about 2/3 of the power left. You'd still have that 83 amps doing that circle, that cycle, all the way through the wire back to the dam. The voltage in your house would be down to about 78 volts. That would be horrible. The light bulbs would be dim, the fridge would have trouble running, be very hard on electronic items. So that would not be a good situation. So we got to look at this and figure out what went wrong. And the answer is here. I mean, yeah, you could say, oh, we need better wires, but that can get very expensive. But the problem is with this 83 amps. Why are you trying to get so much current through this story? And our answer was, well, we were trying to get up to 10,000 watts. Yeah, but P equals IV, I can still get to 10,000 watts. But if you let me send it down across the countryside at a higher voltage, I can do it at a much lower current, because it's this current right here that's really, really hurting us. So let's look at a different option. If we were to think about this in terms of our shopping analogy, we've been using this all along through Physics 11 and 12, so this is our final day where we can use it. We've got this classic story where we said that a battery's like a bank, the customers are like the coulombs, an ammeter is like a little flow meter to measure the customers, and then you've got your house, right, where the voltage is going to get dropped. Well, let's take the ammeter out of there, and let's think about the wire as being like a little Girl Guide store, right? That's just trying to sell you some cookies. And the faster you go through their store, the more money you have to spend. That was the way our shopping analogy always worked. So what have we got? Looking back at the numbers, man, this is interesting. You've got $120 on board every customer, right? $120 per customer, or joules per coulomb. And the flow rate, okay, the customer flow rate is really, really, really high. You've got this 83 customers per second. So the Girl Guides are laughing, right? There are 83, look at them all. There are 83 customers running by every second. Each one of them has 120 volts. And the Girl Guides are like, really? You want to go this fast through here? Oh, you're going to have to pay. And we're losing what was it, about $40, right? Every customer is like, oh, I'm in such a hurry because we're at such a high flow rate. I got to spend $40 on cookies, right? So we got to find a way to deliver $10,000 per second to this house to this store and trick the Girl Guides so that they don't take too much of our money. And we can't be in a hurry. So instead of having 83 customers every second go by with $120, let's change it up. Let's get some really calm customers here who will walk down the road and not let on that they have a bag full of cash. So in their bag, this person might have not $120. Let's give them $120,000. And at that rate, if every customer has $120,000 and you're trying to get $10,000 every second down the road, we don't even need one customer per second. We could do one customer every 12 seconds. So they're calmly walking down the road. And they walk by the Girl Guides. The Girl Guides don't know you've got $120,000 in here. And you're just like, no, I'm not in a hurry. And you won't have to spend very much money. And then it's like 12 seconds later when the next customer comes by. And the Girl Guides are like, oh, it's really slow business today, right? They don't know how much money you've actually got inside that bag. So here it is, last page. Here's what happens. We use a transformer right at the dam to step the voltage up. I'm just going to say by 1,000. And then before we get to your house, we're going to step it down by 1,000. Truth be told, the city of Penticton doesn't do that step down all at once. It does it once when it first comes into town to a slightly safer voltage, and then again just before it goes into your house to get it all the way down to the 120. So the numbers, if we still want 10,000 watts, if you're willing to send it across the countryside at 120,000 volts, if you just do the P equals IV calculation backwards, you can get away with 83 milliamps, right? 1,000 times less. And you might be thinking, oh, well, that means that I guess we'll have 1,000 times, better loss in our story. No, it's better than that, because the equation for the loss of heat, it's actually I squared R. So when you make the I go down by a factor of 1,000, the I squared actually goes down by a factor of 1,000,000. So instead of 3,500 watts, we're talking about 0.003 watts. We're talking about milliwatts. In this story, with these numbers, it's not even worth talking about. So at the house, once you've stepped it back down, you would still have all of your 10,000 watts because you've only lost like 3 milliwatts. It's not even worth talking about. And so that's how they do it. That's why they have these big towers, because they need the wires to be farther up away from people where it's safe, right? Because these wires might have easily 120,000 volts on them. In fact, larger than that's pretty common. 170,000, 240,000. These are reasonable voltages for power transmission lines, and we do that because we really, really want the current to be small. If we can keep the current small, then the losses are tiny. Now, just a couple last little trivia pictures here. If you look at a typical power line around town, I just want to point out what's going on with the various wires that are on the pole. The ones near the bottom are actually the telecommunication ones. That could be cable TV or telephone connections, right? They're all dangerous to some level, but these are probably the least dangerous. And they're down here so that the telecommunication workers can just climb up to there and make their adjustments. And then farther up the pole, we put the more dangerous voltages where you're actually distributing some power. So on this power line, this is actually out in Naramata, you've got 0 volts on this wire. It's actually connected to ground with a little wire that runs down the pole and literally goes into a stake into the ground. And then the feeding voltage here is 7,200, and it goes in, so I've drawn that in red, it goes into this transformer. So my red wires would be connected to the primary coil in this transformer, and then the output, the secondary, goes off to people's homes. Now, I've just said that it's 120 volts. It's a little more complicated than that. There are actually kind of a pair of 120 volt lines there, and power people would tell you that they're out of phase. So when you put them together in a creative way, you can get 240 volts. But let's just say 120, because most of the stuff in your house runs at 120. Notice that this 7,200 volt line is actually quite thin compared to the 120 volt line, and that's because of the currents that are on them. The 120 volt line might have that 83 amps on it, but this thinner line would have much, much less current. So what's interesting is this thin line is actually for the entire block. A whole section of homes are running off this thin wire, but at a high voltage, and these wires are just for one house, right? So you can see that you definitely have to have the thicker wires where the current gets large. Now, last thing, you may be wondering, what's the deal with birds? How can they go and land on this 7,200 volt wire and not be electrocuted? You might think, oh, maybe it's just insulated, it's got a covering on it. Well, actually it doesn't. This wire up here, just for economy, it's not got any insulation on it because nobody should be up there touching that wire, right? And then you're like, oh no, what about the birds? Well, look at its feet. Both feet are touching the same 7,200 volts. So there's no voltage difference from foot to foot. So this bird is totally fine, even though it's at this 7,200 volt alternating voltage level, because no part of it is actually attached to ground. Now, if this bird had very long legs and could grab this wire and that wire at the same time, that would not be a good thing for the bird. And you might go, oh, ha, 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 that'll never happen. Well, it does sometimes happen when birds land on the transformer, because this transformer case is connected to this 0 volt line. And sometimes they will look over at this wire here and go, huh, I wonder how that tastes, and they'll try to bite it. And it does happen once in a while, and it's instantly bad for the bird, because then it would have 7,200 volts across its body from its feet to its beak, instantly fatal. But if it just sits on this one wire, it's totally fine, because both of its feet are at that 7,200 volts. It is alternating, but they're both at that alternating voltage, and there's no difference in voltage on the bird. So everybody's happy. The bird can be happily sitting on the wire, and you can happily know why that bird is happy and why it's okay and why we have these transformers there, right? It's so that we can keep the current down, and it's all about electricity and magnetism. So that's it. That finishes up Physics 12. Congratulations, you've made it to the end. That's our final video and final chapter for Physics 12.